Hello and welcome back to the channel. In this lesson we're going to be learning about the ratio test. The ratio test is an important test for determining whether an infinite series converges or diverges. And with all these tests we have so many of them because there's different types of series, and some tests are useful for different types of series. The ratio test in particular can be useful when we have a factorial, like an n factorial. Looks like n with an exclamation mark. So the ratio test says that if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n equals L, or infinity, the series converges absolutely if L is less than 1, and it diverges if L is greater than 1. Or if L is infinity. Now, if a series converges absolutely, that just means that the absolute value converges. And if the absolute value converges, that means the series itself also converges. Okay? So basically, you have this ratio here, and you're taking the limit as n goes to infinity of the ratio. And on the top of the fraction you have a sub n plus 1, and then on the bottom you have a sub n, and you take the absolute value of that. And you figure out what that equals to. You find that limit, and then if the limit is less than 1, it converges. If the limit is greater than 1, it diverges. Okay, so let's see an example. Example: determine whether each series converges or diverges. Determine whether each series converges or diverges. Okay, my writing is getting messy. That's because I'm tired. Okay, so for number 1, we're going to be doing the sum from n equals 1 to infinity of 8 to the n divided by n factorial. Okay, the sum from n equals 1 to infinity of 8 to the n divided by n factorial. Okay, so for this one, we're going to be using the ratio test. So the first thing we do is we write down the ratio. So remember what we're starting with here, the 8 to the n over n factorial. This is a sub n. And for the ratio test, you take the limit as n goes to infinity of a sub n plus 1 over a sub n with an absolute value around it. Okay, so that's the ratio test. So here what we want to do is, we already know a sub n, and then for a sub n plus 1 in the numerator, you just replace every single n you see with an n plus 1 instead. So what is that going to look like? Well, you've got the n there and the n factorial on the bottom. So instead of 8 to the n over n factorial, we're going to have 8 to the n plus 1 over n plus 1 factorial. Okay, so that's going to look like this. We're going to have the limit as n goes to infinity of 8 to the n plus 1 over n plus 1 factorial all over 8 to the n over n factorial. Okay, so the limit as n goes to infinity of 8 to the n plus 1 over n plus 1 factorial all over 8 to the n over n factorial. And of course we have an absolute value around this. You don't usually end up needing the absolute value, but sometimes you do, so it is important to write it just as a good habit. Okay, and then for all this, we know that we know that if you write an exponential 8 to the n plus 1, that's actually the same as 8 to the n times 8. Okay? So important note. Note that 8 to the n plus 1 equals 8 to the n times 8. Because if you think about it, they have the same base. So 8 to the n times 8 is the same as 8 to the n times 8 to the 1. Okay, so that's going to be, if you multiply the same bases, you add the exponents, you get 8 to the n plus 1. And then the other thing I wanted to talk about, the other trick here, is to realize that n plus 1 factorial is the same as n plus 1 times n factorial. Okay, so n plus 1 factorial equals n plus 1 times n factorial. And if you don't remember factorial from one of your other courses, the basic idea with a factorial is with a factorial you start at the number that you're at, and then you multiply by each smaller number, going all the way down to 1. Okay? So that's why n plus 1 factorial is the same as n plus 1 times n minus 1 times n minus 2, all the way down to 3, 2, 1. Okay? So n plus 1 factorial is equal to n plus 1 times n factorial. Because this n factorial is just going to be n times n minus 1 times n minus 2, going all the way down to 1. So with these two bits of information, we can replace this stuff here. And those are the tricks to these problems. Okay, so what we've got is the limit as n goes to infinity of absolute value of 8 to the n times 8 divided by n plus 1 times n factorial, n plus 1 times n factorial, and then this is all over 8 to the n over n factorial. And then we can cancel out a bunch of stuff here. So we'll notice that we have an 8 to the n here and an 8 to the n there. So one in the numerator, one in the denominator, so those cancel out. And then we also notice that we have an n factorial in this denominator and an n factorial in that denominator. So since we're dividing them, those n factorials cancel out. So really all we're left with that we didn't cross out is 8 over n plus 1. Okay, so here we just have the limit as n goes to infinity of 8 over n plus 1 with an absolute value around it. Okay, and then to find this limit, remember that if you have a limit like this, you can divide the top and the bottom by the highest power in the denominator. Okay, so if we go ahead and multiply on the top and the bottom by 1 over n. Okay, so if we multiply on the top and the bottom by 1 over n, then what's that going to give us? Well, on the top we're going to have 8 over n, and on the bottom we're going to have 1 plus 1 over n. And if we take the limit as n goes to infinity, the 8 over n is going to go to 0 on the top, and then on the bottom the 1 over n is also going to go to 0. So this one goes to 0. So we really have 0 over 1, which is 0. Okay, so we've got 0 over 1, which equals 0. Now what does this tell us? Well, if we scroll back up to the test that we're using, we said that it converges absolutely, which means it also converges, if L, which is the limit, is less than 1. So here, here our L is actually 0, and 0 is definitely less than 1. Okay, so this is L. Okay, so since we have L equals 0, and that's less than 1, that means sum of A sub n converges absolutely. Now the converges absolutely just means that the absolute value of the series converges, but it turns out in math that if a series converges absolutely, it also converges. Okay? All right. So we saw that we were in case 1 here. So since L was less than 1, it converges absolutely, which means it also converges. So here are A sub n. When I said the sum of A sub n converges, I mean this original sum of a to the n over n factorial. Now if you get a number for L that's bigger than 1, including infinity, it can also be positive infinity, then that means that your series diverges. And it doesn't say it here, but if L equals 1, then the ratio test doesn't tell you anything. Okay? So if you get L equals 1, you don't know whether it converges or diverges. We say that the test is inconclusive if L equals 1. Pretty cool, huh? Okay, so that was example number 1. So let's take a look at example number 2 of using the ratio test. So for this next one, we don't actually have a factorial. But the ratio test is what you use generally whenever you have a factorial. Always think of using the ratio test. But this next problem is another example of where you would want to use the ratio test. So for this one, we have the sum from n equals 1 to infinity of n to the 8 over parentheses negative 8 parentheses I can't talk anymore. Negative 8 parentheses to the nth power. Okay, so we have the sum from n equals 1 to infinity of n to the 8 over parentheses negative 8 raised to the nth power. Okay, so we want to use the ratio test here. And the reason it's smart to use it here is you're going to notice that this negative 8 to the n is really hard to determine convergence any other way. But we're going to see that the negative 8 to the n plus 1 can be rewritten just like we did in the last problem, right? Rewrite it as negative 8 to the n times negative 8, and then a bunch of stuff's going to cancel out. Okay, so we're going to do the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Okay, so that's going to be the limit as n goes to infinity of the absolute value of n plus 1 parentheses to the 8th power over negative 8 parentheses to the n plus 1 power all over n to the 8 over parentheses negative 8 to the n power. Okay, and then what do we do from here? Well, just like in the last problem, we want to rewrite the numerator so that we have stuff that's going to cancel out. Now this time we don't have a factorial, but we have a couple of powers here. So first of all, with the n plus 1 to the 8, we can't really rewrite that much. Like you can't write it as n plus 1 times n to the 8, because that wouldn't make sense. So we're going to leave that one that way. But when we look at the negative 8 to the n plus 1, when we look at this one, we are going to be able to cancel that one out. So remember that negative 8 to the n plus 1 is going to equal negative 8 to the n times negative 8. So we are able to simplify that one. Okay, so our limit is now going to become the limit, let me give myself a lot of room, the limit as n goes to infinity of the absolute value of, here we have n plus 1 to the 8 over negative 8 to the n times negative 8 all over n to the 8 over negative 8 to the n. Okay, so we have n plus 1 to the 8 over negative 8 to the n times negative 8 all over n to the 8 over negative 8 to the n. All right, so so far all that's going to cancel out at this point is we've got this negative 8 to the n in this denominator and that negative 8 to the n on the bottom denominator, and those two are going to cross out. And then this negative 8 in this denominator, we can kind of factor that out front as a negative 1/8 and keep it inside of the absolute value. Okay, so what we got so far is the limit as n goes to infinity of absolute value of negative 1/8 times, we have n plus 1 to the 8th in the numerator and n to the 8th in the denominator. So now the trick here is to notice that for this fraction, we actually have an 8 for both of those exponents. So we can actually kind of factor that 8 out here into the exponent. So I'm going to go ahead and sort of factor out the 8th exponent and bring it out here. And then you'll see in a second why that's a good idea. So what that's going to look like is now we took those 8 as the exponents and we brought them out here. So what we're going to do next is our favorite thing to do whenever we're doing an infinite limit and you have a rational expression or a fraction. We like to multiply the top and the bottom by 1 over the highest power in the denominator. Okay, so here, inside of this exponent, I'm actually going to multiply the top and the bottom of this fraction by 1 over n. Because n is the largest power in the denominator. Okay. And so then everything else is going to be the same, but a bunch of stuff's going to simplify now. So we're going to have limit as n goes to infinity of absolute value of negative 1/8 times, distributing the 1 over n on the top, we get 1 plus 1 over n over n times 1 over n is 1. So we have 1 plus 1 over n, parentheses raised to the 8th power. Okay, and then that's all over 1. Alright, so what's going to happen there is any number divided by 1 is just a number, so we don't need to divide by 1. So we can erase that. And then for the 1 plus 1 over n to the 8, we can still kind of plug in infinity there, and we know that 1 over n, as n goes to infinity, 1 over n is going to go to 0. Okay, so this is just going to go to 0. So actually a lot of stuff simplifies now. So, so all we're really left with is absolute value of negative 1/8 times 1 to the 8. Okay, and we already plugged in n is infinity, and that gave us 0 for the 1 over n up here. And then 1 to any power is just 1. So this is just 1. And so really we just have the absolute value of negative 1 over 8. And remember, absolute value is always positive. So it takes a negative number and makes it positive. So this one's going to become positive 1/8. Okay? And this is actually going to be our L that we got from the ratio test. So L equals 1/8 Okay, and because 1/8 is actually less than 1, by the ratio test, we know that the series converges absolutely. Okay, so since 1/8 is less than 1, L equals 1/8, which is less than 1, the series converges absolutely. So the sum of a sub n converges absolutely. And on some problems they just ask you if it converges. On other ones they ask you if it converges absolutely. So I'll put absolutely in parentheses. But if it converges absolutely, it also converges. It's just the absolutely part is because we took the absolute value in the ratio test. Okay? Cool. So I wanted to take on an even harder problem for number 3. Okay, so this next one is example number 3. So for this one, the difficulty is getting to be more. Here we have the sum from n equals 1 to infinity of -1 to the n times the fraction n squared times n plus 6 factorial all over n factorial times 8 to the 3n. Okay, so the sum from n equals 1 to infinity of -1 to the n times n squared times the quantity n plus 6, quantity factorial, all over n factorial times 8 to the 3n. So this one is challenging just because it has so much going on. But we're still going to be using the ratio test. Okay? So we're still going to do the limit as n goes to infinity of the absolute value of a sub n plus 1 over an. Okay? It's just here there's going to be a lot of stuff that we have to work with. So here we've got the limit of the absolute value. Well, our numerator is going to be -1 to the n plus 1 times n plus 1 quantity squared times n plus 7 factorial. Now, how did I get n plus 7? Well, n plus 1 plus 6 is n plus 7. So that's how I got n plus 7 factorial. And then our denominator is going to be n plus 1 factorial times 8 to the 3 times n plus 1 with parentheses around it. So this one's quite a bit more challenging than the earlier ones. And notice when I'm plugging in the n plus 1 for the 8 to the 3n, I put parentheses around the n plus 1. That is important. Okay? And that is our numerator. And then our denominator is just going to be the same expression that we started with. So this right here, this whole thing is our a sub n. Okay, so we're going to be dividing by that. So our denominator is going to be -1 to the n times n squared times n plus 6 factorial all over n factorial times 8 to the 3n. So the hardest thing about this problem is just keeping track of everything. It's just such a huge mess here. But let's see how we can do with this. So once again, we want to set up everything so everything's going to cancel out. So for the -1 to the n plus 1, that one we can rewrite as -1 to the n times -1. Okay, so let me give myself lots of room here. We've got -1 to the n times -1. And then for the n plus 1 squared, we're just going to leave it that way. So we're still going to have an n plus 1 squared here. For the n plus 7 factorial, we can write that as n plus 7 times n plus 6 factorial, because we know that n plus 6 factorial is going to cancel with this one down here. Okay, and then in our denominator here, the n plus 1 factorial can be rewritten as n plus 1 times n factorial, and that n factorial is going to cancel out. And then right here, we've got 8 to the 3n plus 3. If we go ahead and distribute that 3 to each of those terms. And 8 to the 3n plus 3 is the same as 8 to the 3n times 8 cubed. So I'm going to rewrite this. Instead of 8 to the 3n plus 3, I'm going to write it as 8 to the 3n times 8 to the third. Because remember, if you're multiplying exponentials with the same base, you add the exponents. So that actually gives you 8 to the 3n plus 3. But now I'm going to be able to cross out the 8 to the 3n on the top and the 8 to the 3n down there. Okay, and of course the rest of this limit is still the same. Okay, so our denominator hasn't changed, so it's still going to be negative 1 to the n times n squared times n plus 6 factorial all over n factorial times 8 to the 3n. Now this is a very ugly problem because there's just so much going on. But stuff is now going to cancel out. So we can see that we have this negative 1 to the n there and a negative 1 to the n down there. So those cross out. And then beyond that, we also have an n plus 6 factorial on the top right, and then an n plus 6 factorial down here. So these cancel out. And then in this denominator, we have an n factorial, and we also have one down there. So these two cross out. And then, of course, the 8 to the 3n's also cross out. Okay, so what are we left with? Well, we're left with whatever we didn't cross out, which is still quite a bit here. So we still have the limit as n goes to infinity. Now what we've got is absolute value of negative 1 times n plus 1 squared times n plus 7 over n plus 1 times 8 cubed. And what's 8 cubed? 8 times 8 is 64. And then what's 8 times 64? Oh, I don't know. I should probably know that. But 8 times 64 is 512. Okay. So in our denominator, we have a 512. And then don't forget, we also have this n squared down here. So if we flip that over, that n squared, because we're dividing by it, is going to end up, dividing by a fraction means multiplying by the reciprocal, so that n squared is going to go up here. So why don't I go ahead and write the n squared right there. Okay. And yeah, this is a very ugly problem. It just has a lot of stuff going on. I don't like to do a lot of these, especially in an online class, but I should probably do one once in a while just to keep us honest. Okay? So we're going to notice something else cancels out here now. We notice that we have an n plus 1 squared on the top and an n plus 1 on the bottom. So the square and the n plus 1 cancel out, and we're left with an n plus 1 on the top. And then we can factor out this negative 1 over 512. Okay, so we have the limit as n goes to infinity of absolute value of negative 1 over 512 times, well, what do we have left here? We have n plus 1 times n plus 7 over n squared. Right, that's what we have left. Okay, and then to find this infinite limit, you want to go ahead and multiply out the n plus 1 times n plus 7. We can multiply that out with FOIL. Okay, so using FOIL here in the numerator, we get n squared plus 7n plus n. So that's going to be n squared plus 8n plus 1 times 7 is 7. Okay, so we have n squared plus 8n plus 7 all over n squared. And then since we're doing an infinite limit, once again we want to multiply the top and the bottom by 1 over the highest power in the bottom. So we're going to be multiplying this entire fraction here by 1 over n squared on the top and the bottom. Okay, and of course we're still finding the limit as n goes to infinity at the absolute value of negative 1 over 512 times this whole thing. So this is a hard problem, I'm not going to lie. It's hard. Just a lot going on. But good thing I'm doing one that's very similar to your homework. Okay? And then all we have left to do is distribute this 1 over n squared to the numerator and denominator. So when we multiply by 1 over n squared and we distribute on the top, we're going to end up with 1 plus 8 over n plus 7 over n squared. All over on the bottom, the n squareds cancel, so we just have 1. And then of course, since we're taking the limit as n goes to infinity, 8 over n and 7 over n squared, these are both going to go to 0. Okay, so really for this whole thing, all we have is 1 over 1, which is 1. Okay, and we've already plugged in that limit as n goes to infinity here. So really all we're going to be left with is negative 1 over 5/12 with an absolute value around it. So negative 1 over 5/12 with an absolute value around it. And of course the absolute value of a negative number is the positive number. So this is going to give us positive 1 over 5/12. Which is pretty cool, I think. It was such a complicated problem, but we ended up having everything simplified down to a single number. Okay, and because 1 over 5/12 is our limit, and because our limit L is less than 1, that means the series converges absolutely. The series converges absolutely. Okay, pretty cool, huh? So that was a tough one. I like to do one of those once in a while. Okay, so I wanted to show you a couple more examples of the ratio test. So the one we just did was pretty long. That's about the hardest one on your homework, something like that. That was number 3. So let's take a look at example number 4. So for example number 4, this one's a little bit easier. Here we have the sum from n equals 1 to infinity of n to the root 2. Okay, so n to the root 2 over 15 to the n. Now, as long as you know how to deal with n to the root 2, this is actually a lot easier problem. But the n to the root 2 is probably the only part that might throw you off a little bit. So, using the ratio test, we're taking the limit as n goes to infinity of a sub n plus 1, so absolute value of a sub n plus 1 over a sub n. So here, we're going to have the limit of, well, our numerator is going to be n plus 1 quantity to the root 2 over 15 to the n plus 1. And this is all over n to the root 2 over 15 to the n. Okay, so kind of the same setup as a lot of the earlier problems. The only thing that's a little bit weird is the n plus 1 to the root 2 and the n to the root 2. That might be the only thing that might throw you off a little bit. Okay, so what do we do with that stuff? Well, remember that for the 15 to the n plus 1, we can rewrite that as 15 to the n times 15. So we can do that. So what do we got here? We've got the limit. Actually, let me write it down below. We've got the limit as n goes to infinity of n plus 1 to the root 2 over 15 to the n times 15. And then this is all over n to the root 2 over 15 to the n. Okay, and then we have an absolute value around this whole thing. Okay, so now the 15 to the n in each denominator, those are going to cancel out. Okay, so these cross out. And we just have a 1 over 15 left over, so we can bring that out front. Okay, so we have the limit as n goes to infinity of absolute value of 1 over 15 times n plus 1 to the root 2 over n to the root 2. Okay, and even though we have this strange exponent, which is actually the square root of 2, because these exponents are the same, we can actually factor the root 2 outside of the fraction. Okay, so in other words, since the numerator and the denominator both have root 2 as the exponent, we're able to factor that root 2 out to the exponent in the front. Okay, so it actually goes here. Okay, so we have the limit as n goes to infinity of absolute value of 1 over 15 times parentheses n plus 1 over n, quantity to the root 2. So all I did there was I factored out the root 2 of the exponent. I factored that out to this exponent here. And then once you have a fraction like this, you always want to multiply the top and the bottom by 1 over the highest power in the denominator. Okay, so we're going to go ahead and multiply this fraction by 1 over n on the top and the bottom. Okay, so now we're going to have the limit as n goes to infinity of the absolute value of 1 over 15 times parentheses, distributing the 1 over n, we're just going to get 1 plus 1 over n. And then on the bottom, the n's cancel and we just get 1. And then this is raised to the root 2 power. But it turns out that the root 2 power isn't going to even matter, because when we plug in infinity here, the 1 over n is going to go to 0. So we really just end up with absolute value of 1/15 times 1 to the root 2, which is kind of similar to what happened in an earlier problem. It's just we have this weird exponent of square root of 2. But remember, root 2 is just a real number. It's a decimal, but it's still a number. And 1 to any number is 1. Okay, so this right here, 1 to the root 2, that's just 1. So we really just have the absolute value of 1/15. And because 1/15 is already positive, the absolute value doesn't do anything. So our answer is going to be 1 over 15. And that's our L. That's the limit. Okay, so by the ratio test, since L equals 1 over 15, which is less than 1, that means the series converges, absolutely. Okay, the series converges absolutely. Alright, so I think you've seen almost all the tricks. In fact, I believe you have seen all the tricks. So I think you're going to be good for your homework now. So thanks for watching all the way to the end, and have a good day.